Magnetic effect of electric current. Electrical current has two effects. First one is heating effect, and second one is magnetic effect. In the previous chapter on electricity, we learnt about the heating effect of electric current. What could be the other effect of electric current? We know that an electric current carrying wire behaves like a magnet. Isn't that very interesting? So let us study in this lesson about magnetic effect of electric current. One of the leading scientists of the 19th century, Hans Christian Ørsted, played a crucial role in understanding electromagnetism. In 1820 he accidentally discovered that a compass needle got deflected when an electric current passed through a metallic wire placed nearby. What does it mean? It means that the electric current through the copper wire has produced a magnetic effect. Then, we can say that electricity and magnetism are linked to each other. Then, what about the reverse possibility of an electric effect of moving magnets? In this chapter, we will study magnetic fields and such electromagnetic effects. We shall also study about electromagnets and electric motors, which involves the magnetic effect of electric current, and electric generators, which involves the electric effect of moving magnets. Magnetic field and field lines. Now let's see magnetic field and field lines. We are familiar with the fact that a compass needle gets deflected when brought near a bar magnet. A compass needle is, in fact, a small bar magnet. The ends of the compass needle point approximately towards north and south directions. The end pointing towards north is called north-seeking or north pole. The other end that points towards south is called south-seeking or south pole. Through various activities, we have observed that like poles repel, while unlike poles of magnets attract each other. Means, magnets went to like poles, the North Pole and the North Pole, or the South Pole and the South Pole come together, they repel. On the other hand, unlike poles, the North Pole and the South Pole come together, they attract each other. Let us perform activity 13.2. Fix a sheet of white paper on drawing board. Place a bar magnet in the center of it. Sprinkle some iron fillings uniformly around the bar magnet. If we observed here, the iron fillings arranges themselves in a pattern. Why do the iron fillings arrange in such a pattern? What does the pattern demonstrate? The magnet exerts its influence in the region. Thus exerted makes iron fillings to arrange in a pattern. The region surrounding a magnet, in which the force of the magnet can be detected. If we draw a diagram of this on a paper, it will look like this. The long curved lines shown along the magnet are called the magnetic lines of force. They run from the North Pole to the South Pole. The space in which the lines of force are spread around a magnet is called the magnetic field. The characteristics of the lines of force are, they attempt to form closed loops from pole to pole. They never intersect. They all have the same strength. The number of lines of forces per unit area determines the strength of magnetic field at that point. due to a current in a solenoid. Solenoid, a coil of many circular turns of insulated copper wire, wrapped closely in the shape of a cylinder, is called a solenoid. Whenever an electric current passes through a solenoid, magnetic field lines are produced. Compare the pattern of the field line with the magnetic field around a bar magnet. Do they look similar? Yes, they are similar. In fact, one end of the solenoid behaves as a magnetic north pole, while the other behaves as the south pole. The field lines inside the solenoid are in the form of parallel straight lines. This indicates that the magnetic field is same at all points inside the solenoid. That is, the field is uniform inside the solenoid. But how to find the north pole and south pole of solenoid? At the one end of the solenoid, if the current flow anti-clockwise, then that end is north pole. And on the other end of the solenoid, current flow clockwise is considered as south pole. A strong magnetic field produced inside a solenoid can be used to magnetize a piece of magnetic material like soft iron when placed inside the coil. The magnet so formed is called an electromagnet. Right-hand thumb rule. A convenient way of finding the direction of magnetic field associated with a current-carrying conductor is right-hand thumb rule. Imagine that you are holding a current-carrying straight conductor in your right hand, such that the thumb points towards the direction of current. Then your fingers will wrap around the conductor in the direction of the field lines of the magnetic field. This is known as the right-hand thumb rule. For a straight current-carrying wire, the magnetic field lines are in form of concentric loops. If the wire is carrying current in an upward direction, the direction of magnetic field is in anti-clockwise direction, but if the wire is carrying current in a downward direction, the direction of magnetic field is in a clockwise direction. Magnetic field due to a current through a circular loop. So far we have studied that when current is passed through a straight conductor, a magnetic field is produced around the conductor. This region of magnetic field can be represented as concentric circles around the wire. The direction of these lines of force can be found by the right-hand thumb rule. Now, instead of a straight conductor, we can take a circular loop. How would the magnetic field lines look like? Let's do an activity for the better understand. Take a rectangular cardboard having two holes. Insert a circular coil having number of turns through them, normal to the plane of the cardboard. Connect the ends of the coil in series with a battery, a switch, and a rheostat. Sprinkle iron filings uniformly on the cardboard. Turn on the switch. We can see that the directions of the current flowing through each arm of the circular loop are mutually opposite. Now, tap the cardboard gently a few times. Note the pattern of the iron filings that emerges on the cardboard. These circles prove the presence of a magnetic field. We know that the magnetic field produced by a current-carrying straight wire depends inversely on the distance from it. Similarly, at every point of a current-carrying circular loop, the concentric circles, representing the magnetic field around it, would become larger and larger as we move away from the wire. By the time we reach at the center of the circular loop, the arcs of these big circles would appear as straight lines. Every point on the wire carrying current would give rise to the magnetic field appearing as straight lines at the center of the loop. By applying the right-hand rule, it is easy to check that every section of the wire contributes to the magnetic field lines in the same direction within the loop. According to this rule, we can find that the direction of the magnetic lines of force around the arm of the conductor with upward flow of current is anti-clockwise, while that around the arm of the conductor with downward flow of current is clockwise. We know that the magnetic field produced by a current-carrying wire at a given point depends directly on the current passing through it. Therefore, if there is a circular coil having n turns, the field produced is n times as large as that produced by a single turn. This is because the current in each circular turn has the same direction, and the field due to each turn then just adds up. Force on a current-carrying conductor in a magnetic field. We have learned that an electric current flowing through a conductor produces a magnetic field. The field so produced exerts a force on a magnet placed in the vicinity of the conductor. A French scientist, André-Marie Ampère, suggested that the magnet must also exert an equal and opposite force on the current-carrying conductor. The force due to magnetic field acting on a current-carrying conductor can be demonstrated through the following activity. To perform this activity, we need small aluminium rod of about 5 centimeters, 2 connecting wires, and strong horseshoe magnet. Place a strong horseshoe magnet in such a way that the rod lies between the two poles with the magnetic field directed upwards. For this, put the north pole of the magnet vertically below and south pole vertically above the aluminium rod. Connect aluminium rod to a circuit in series with the battery and switch. The conductor is placed between the poles of a strong horseshoe of a magnet. Now pass a current through the aluminium rod from end B to end A and observe. We can observe that the conductor wire displaced towards left side. The displacement of the rod suggests that a force is exerted on the current-carrying conductor. Reverse the direction of current flowing through the rod by reversing the battery polarity and observe. we can see that the conductor now get displaced towards right side, which means the direction of the force is reversed. The displacement of the rod in the above activity suggests that a force is exerted on the current carrying conductor when it is placed in a magnetic field. It also suggests that the direction of force is also reversed when the direction of current through the conductor is reversed. It shows that the direction of the force on the conductor depends upon the direction of current and the direction of the magnetic field. In this activity, we considered the direction of the current and that of the magnetic field perpendicular to each other, and found that the force is perpendicular to both of them. The three directions can be illustrated through a simple rule called Fleming's left-hand rule. According to this rule, stretch the thumb, forefinger, and middle finger of your left hand such that they are mutually perpendicular. If the first finger points in the direction of magnetic field and the second finger in the direction of current, then the thumb will point in the direction of motion or the force acting on the conductor. Devices that use current-carrying conductors and magnetic fields include electric motor, electric generator, loudspeakers, microphones, and measuring instruments. Electric motor. In today's session, we will discuss the construction, working, and applications of an electric motor. Why do we need to learn about electric motor? Because electric motor is a rotating device that converts electrical energy to mechanical energy. This makes the electric motor an important component in electrical fans, refrigerators, mixers, washing machines, computers, MP3 players, etc. Now, let's see how the electric motor works. The electric motor works on the principle of force experienced by a current-carrying conductor in a magnetic field. Now, let's set up the simple electric motor. An electric motor consists of a rectangular coil of copper wire. Let's label it as ABCD. This rectangular coil is situated in between the two poles of a magnetic field in such a way that arm AB and CD is perpendicular to the magnetic field. The two ends of the coil are connected to the two halves of a split ring. Let's label them as P and Q. The inner sides of these halves are insulated and attached to the axle. The external conducting edges of P and Q touch the two conducting stationary brushes X and Y, and these stationary brushes are connected to a source called a battery. So, this is how the complete setup of a simple electric motor looks. Now, let's understand how it works when the switch is on. The current enters into the coil ABCD from the source battery through conducting brush X and flows back to the battery through brush Y. Notice that the direction of current is flows from A to B in the arm AB and C to D in the arm CD. That is, in the opposite direction to current flow in AB. We know that when a current-carrying conductor is placed in an external magnetic field, it experiences a force on it. And the direction of force can be found by using the Fleming's left-hand rule. On applying Fleming's left-hand rule for the direction of force on a current-carrying conductor in a magnetic field, we find that the force acting on arm AB pushes it downwards, while the force acting on arm CD pushes it upwards. As a result of these two forces, the coil and the axle O, mounted free to turn about an axis, rotate anti-clockwise. At half rotation, Q makes contact with the brush X, and P makes contact with brush Y, resulting in the direction of current in the coil being reversed. Therefore, the current in the coil gets reversed and flows along the path DCBA. A device that reverses the direction of flow of current through a circuit is called a commutator. In electric motors, the split ring acts as a commutator. The reversal of current also reverses the direction of force acting on the two arms AB and CD. Thus the arm AB of the coil, that was earlier pushed down, is now pushed up, and the arm CD, previously pushed up, is now pushed down. You can again verify it using the Fleming left-hand rule. The arm may be off. The coil that was pushed downward earlier is now pushed in the upward direction, and the arm CD pushed up earlier is now pushed down. Therefore the coil and the axle rotate half a turn, move in the same direction, and when it completes its full rotation, is reversed at every half rotation, giving rise to a continuous rotation of the coil and to the axle. This is how all about working of an electric motor. It converts the electric energy to the mechanical energy. Rotation of speed or power of electric motor depends upon the so many factors. First, we can try to increase the number of rotations. For this, we have to increase the number of turns of the coil. Second, to increase the strength of the magnetic field, we can use more powerful magnets. The commercial motors uses are: first, an electromagnet in place of permanent magnet. Second, large number of turns of the conducting wire in the current-carrying coil. And third, a soft iron core on which the coil is wound. The soft iron core on which the coil is wound, plus the coils, is called an armature. This enhances the power of the motor. Electromagnetic induction. Electromagnetic induction is the process of generating electric current with a magnetic field. It occurs whenever a magnetic field and an electric conductor, such as a coil of wire, move relative to one another. As long as the conductor is part of a closed circuit, current will flow through it whenever it crosses lines of force in the magnetic field. We have studied that when a current-carrying conductor is placed in a magnetic field, such that the direction of current is perpendicular to the magnetic field, it experiences a force. This force causes the conductor to move. Now, let us imagine a situation in which a conductor is moving inside a magnetic field, or a magnetic field is changing around a fixed conductor. What will happen? This was first studied by English physicist Michael Faraday. In 1831, Faraday made an important breakthrough by discovering how a moving magnet can be used to generate electric currents. To observe this effect, let us perform the following activity. We have taken a bar magnet, a coil wire, and a galvanometer. The galvanometer is connected to the coil and is used to detect the current flowing in the conductor. Name the coil wire ends A and B. Take a strong bar magnet and move its north pole towards the end B of the coil. Observe the change in the galvanometer needle. There is a momentary deflection in the needle of the galvanometer, say to the right. This indicates the presence of a current in the coil AB. The deflection becomes zero the moment the motion of the magnet stops. Now, withdraw the north pole of the magnet away from the coil. Now the galvanometer is deflected toward the left, showing that the current is flow opposite to the first. Place the magnet stationary at a point near to the coil, keeping its north pole towards the end B of the coil. We see that the galvanometer needle deflects toward the right when the coil is moved towards the north pole of the magnet. Similarly, the needle moves toward left when the coil is moved away. When the coil is kept stationary with respect to the magnet, the deflection of the galvanometer drops to zero. What do you conclude from this activity? The galvanometer deflects only when the magnet is in motion near the coil. Motion of the magnet is responsible for the changing magnetic field. This changing magnetic field is inducing the current in the conductor. This phenomenon is called electromagnetic induction. Let us study electromagnetic induction with the help of a current-carrying coil. Let us now perform another activity in which the moving magnet is replaced by a current-carrying coil, and the current in the coil can be varied. Take two different coils of copper wire having large number of turns. Coil 1 is called the primary coil, and coil 2 is called the secondary coil. Insert them over a non-conducting cylindrical rod. Connect the primary coil, having larger number of turns, in series with a battery and a switch. Also connect the other secondary coil with a galvanometer. Turn on the switch. Observe the galvanometer for deflection. The needle of the galvanometer instantly jumps to one side, and just as quickly returns to zero. This indicates a momentary current in the secondary coil. Disconnect primary coil from the battery. We can observe that the needle momentarily moves, but to the opposite side. It means that now the current flows in the opposite direction in secondary coil. From these observations, we conclude that a potential difference is induced in the secondary coil whenever the electric current through the primary coil is changing. So we can conclude that the process by which a changing magnetic field in a conductor induces the current in another conductor is called electromagnetic induction. As the current in the first coil changes, the magnetic field associated with it also changes. Thus the magnetic field lines around the secondary coil also change. Hence the change in magnetic field lines associated with the secondary coil is the cause of induced electric current in it. This process, by which a changing magnetic field in a conductor induces a current in another conductor, is called electromagnetic induction. In practice, we can induce current in a coil either by moving it in a magnetic field or by changing the magnetic field around it. It is convenient in most situations to move the coil in a magnetic field. Electric generator. In this section, we are going to learn about an AC generator. An AC generator is an electric generator that converts mechanical energy to electrical energy in the form of an alternating electromagnetic field or alternating current. Working principle of an AC generator. An AC generator works on the principle of electromagnetic induction. In electromagnetic induction, when there is a relative motion between a coil and a magnetic field, an electric current or electromotive force is induced in the coil. Now, let's set up the simple electric generator. An electric generator consists of a rotating rectangular armature or coil ABCD placed between the two poles of a permanent magnet. The two ends of this coil are connected to the two slip rings R1 and R2. These are connected to the armature and thus rotate with it. The inner side of these rings are made insulated. The two conducting stationary brushes B1 and B2 are kept pressed separately on the rings R1 and R2 respectively. The two rings R1 and R2 are internally attached to an axle. The axle may be mechanically rotated from outside to rotate the coil inside the magnetic field. Outer ends of the two brushes are connected to the galvanometer to show the flow of current in the given external circuit. When the axle attached to the two rings is rotated such that the arm AB moves up and the arm CD moves down in the magnetic field produced by the permanent magnet. Let us say the coil ABCD is rotated clockwise in the arrangement. By applying Fleming's right-hand rule, the induced currents are set up in these arms along the directions AB and CD. Thus an induced current flows in the direction ABCD. This means that the current in the external circuit flows from B2 to B1. After half a rotation, arm CD starts moving up and AB moving down. As a result, the directions of the induced currents in both the arms change, giving rise to the net induced current in the direction DCBA. The current in the external circuit now flows from B1 to B2. Thus, after every half rotation, the polarity of the current in the respective arms changes. Such a current, which changes direction after equal intervals of time, is called an alternating current. The abbreviation is AC. This device is called an AC generator. To get a direct current, which does not change its direction with time, a split ring type commutator must be used. With this arrangement, one brush is at all times in contact with the arm, moving up in the field, while the other is in contact with the arm, moving down. We have seen the working of a split ring commutator in the case of an electric motor. Thus, a unidirectional current is produced. The generator is thus called a DC generator. The difference between the direct and alternating currents is that the direct current always flows in one direction, whereas the alternating current reverses its direction periodically. Most power stations constructed these days produce AC. In India, the AC changes direction after every 1/100 second, that is, the frequency of AC is 50 Hz. An important advantage of AC over DC is that electric power can be transmitted over long distances without much loss of energy.